If I asked you where electrical energy travels, most people would point inside the wire, because that's what it looks like. Electrons in copper, energy in copper. But here's the twist. In real electromagnetics, the energy mostly travels in the space around the wire, in the fields, not in the metal. And once you see it, RF starts making sense. DC tricks your brain because everything feels slow and steady. RF is different. At high frequency, the fields matter so much that a wire stops behaving like a simple wire. It becomes a transmission line, a structure that guides electromagnetic energy. Whenever a voltage exists, you get an electric field. Whenever current flows, you get a magnetic field. Those two fields together create energy flow, a real flow described by the Poynting vector. It points in the direction energy is moving.
Here's another mind blower. The electrons drift incredibly slowly. They're not sprinting from the battery to your phone in 1 second. What moves fast is the electromagnetic field, the signal. And that energy flow rides along the structure near the speed of light in the medium. Imagine a battery connected to a resistor. The popular story is energy travels through the wire, reaches the resistor, turns into heat. The field story is the energy flows through the space around the wire and into the resistor from the outside, where it's dissipated.
Now, if you're into RF, this is not philosophy. This is design, because at RF, your wire is literally shaping the fields. And if you shape the fields wrong, you get reflections, loss, crosstalk, EMI.
Let's make it concrete. A coaxial cable. If energy traveled inside copper, coax would make no sense. In a coax, the electric field lives in the dielectric between conductors. The magnetic field wraps around the center conductor, and the energy flow, E cross H, points right down the cable, inside the dielectric region.
Two-wire lines are even more visual. The energy isn't in the copper, it's in the space between the wires, air or insulation. That's why spacing, dielectric, and geometry change impedance. When does a wire stop being a wire? When the physical length becomes a meaningful fraction of a wavelength. Then voltage and current aren't the same everywhere at the same time. They become waves, moving, reflecting, standing.
And when that wave hits a mismatch, energy doesn't just vanish. Part of it continues. Part of it reflects. That reflected energy is real power flowing back, again, in the fields. So, what's inside the conductor? Mostly where energy is lost, resistive heating. That's why, in a good conductor, the electric field inside is small compared to the fields outside. The wire is more like a boundary condition guiding fields than a pipe carrying energy. And at RF, current crowds to the surface. Skin effect. Higher frequency means smaller skin depth. Less of the conductor actually carries current. This is why RF conductors behave differently than DC conductors. Here's where engineers get burned: the return path. Fields don't care about your schematic symbol for ground. They care about the physical path that completes the loop. At RF, return current follows the path of lowest impedance, often right under the signal trace, because that minimizes loop inductance. This is why RF feels like black magic to beginners, because you're not designing wires, you're designing field geometry, spacing, dielectric, planes, shields, bends, connectors. Once you accept that, you stop fighting RF and you start controlling it. So the next time someone says, energy flows through the wire, you can say this instead: the wire guides it. The fields carry it. Once you understand that, RF stops being mysterious and starts being predictable. RF is everywhere. In your phone, in satellites, in medical imaging, in systems that shape the modern world. RF 101 Explained exists for one reason: to make radio frequency engineering clear, visual, and intuitive. If you enjoy understanding how things really work, this channel is for you. Welcome to RF 101 Explained.